Hi, my name is Tim. In this video, I'm going to go over 10 common radio control model airplane mistakes that you can avoid. Let's get to it. In this video, I'd like to go through 10 common mistakes that RC models can make with their RC airplanes. By understanding these situations and learning from them and not having them happen, you may avoid a crash and save some money for your RC model airplane. I've been flying radio control model aircraft for 50 years. I've designed over 20 of my own models, had 6 published in the modeling press. Combined with my time flying full-scale aircraft, I'd like to share with you some insights that might help you have a better job flying your RC model airplanes. When I first started flying radio control model airplanes, everybody had to build their own airplanes. There really weren't any high-quality, ready-to-fly or almost ready-to-fly models. Today, that has significantly changed. The vast majority of RC models, to include myself, fly almost ready-to-fly or ready-to-fly models. They're a good addition to your mix, to your hangar of aircraft, but some commonly used skills like balancing at the center of gravity, selecting the right propeller, etc., have fallen by the wayside a little bit as we more and more just take the kits out of the box and go ahead and fly them at the field. So that thought in mind of the 10 common mistakes you can avoid for your RC model aircraft, I'd like to start with without a doubt, is the most important thing to do, and that is to make sure that the model balances properly at the center of gravity. So what is the center of gravity? The center of gravity is the point in the model. If you can imagine hanging an airplane at that point, the airplane would be balanced. With a straight-winged aircraft like this, the center of gravity is typically about 20 to 25% back from the leading edge of the wing. The center of gravity is a common symbol. It's a circle with 2 sectors filled in. I'll show you an example of the center of gravity up above. You can see it on plans for any type of model airplane. In addition, even for ready-to-fly aircraft like the E-flite Radian, there is a center of gravity listed in the instruction manual, and I'll show that above now as well. And so to find the center of gravity, we literally just put our fingers about 20 to 25% of the way back at the center of gravity on the plans, and the model should balance. If it's down like this at the center of gravity location, it's tail heavy. If it's nose heavy, that means it's nose heavy. It is absolutely imperative that we balance the model at the center of gravity. If you take off, it's typically a tail-heavy situation with the center of gravity because we can build structure into the tail, and it's a distance away from the center of gravity. It tends to be tail-heavy. Whatever you need to do on the model to balance it has to be done if it include adding weight. For the center of gravity in the Aeronca, you are stuck with the length of the nose. I try to build the tail as light as possible, but even on this one, if you just take a peek inside the cowl here, you can see the iron nut that I had to epoxy in place as far forward as possible to keep the center of gravity where it was on the wing. The weight was critical on this, but I had to do that to achieve the proper center of gravity. With other models, like for example, this foam board model, the F-22, there are calculators online to find the center of gravity if you don't have a kit. The center of gravity I know from the plans is at this line right here where the panels join. If I hold it here, you can see it's extremely tail heavy because of the motor in the back. What we do for the design is we take our 3-cell lipo. It's located in the front. When I hold it here, the center of gravity, now the model balances perfectly. It is absolutely imperative that all your models fly balance at the center of gravity. One final illustration of the center of gravity is my square, 20-inch square flying wing design. I designed this, and I just put the center of gravity 20% back at about 5 inches, and I have the center of gravity marked right here. Okay, so it has to balance there. I had to add a little bit of weight to the nose to get to that center of gravity location, even though I had the motor up front. Just a technique as you design and understand the center of gravity, instead of having to add weight, which you don't want to do if not required, I could have easily made the nose a little bit longer. That way the motor would have been further forward. That would have added to the proper center of gravity without additional weight. The next mistake to avoid is try to get an airplane that matches your skill level. In the old days when we built our kits, there was a lot of thought before you went to all the time and effort to build it. If you were a beginning flyer, you would obviously build a trainer. The challenge these days is there are so many high quality, ready to fly kits out on the market. It can be very easy to buy a high performance jet or acrobatic airplane for your first airplane. You just have to start off with a trainer to learn how to fly, then advance up to the other aircraft. Computer-based simulators are very helpful on this. And I speak from experience. The very first airplane I bought when I was back in high school in 1972, U-Control Cox aircraft. There were two models at the hobby store, the plastic Stuka and the PT-19 trainer. Of course, what did I buy? The Stuka, because it looked great with a Cox 049 engine, started up, crashed immediately after takeoff into 100 pieces. Bought the PT-19 trainer, very flexible plastic, easier to fly. Just try not to make that mistake. You'll learn how to fly pretty quickly, and you'll be able to fly the more advanced models that you see in the hobby store, online, and at the field. The next most common mistake is making your airplane too heavy. Each airplane has a design weight when it's designed. And we understand this weight on ounces per square foot for model aircraft. Same for full aircraft, it's just pounds per square foot. And what will happen is for a glider or lighter model is about 4 ounces per square foot. For a sport model, 10 to 12 ounces, probably 20 ounces per square foot is the most you're going to see. What will happen is if an airplane gets heavier than it was designed to be, it'll still fly, but it will have worse performance. Because it's heavy, it'll have to take off much faster. The additional weight will have a higher stall speed. You'll have to land faster. If you land at your normal speed, it may stall out and crash, but it will fly. And so where this could be a factor, you get a almost ready to fly aircraft. There's plenty of room inside. You start adding electronics for cameras, first person view, and so forth. The plane can get heavy. So just keep an eye on the weight wherever possible. It will not be fixed by a bigger motor and more battery power. You will have the power, but the weight will affect the flight characteristics. If you're designing your own airplane, an easy way to fix a plane that's slightly overweight, simply make a bigger wing to reduce the wing loading for that aircraft. Another common mistake is not having the correct propeller for the aircraft. This is pretty easy to fix. Online, we can look up the motor and the range of propellers. Depending on the type of model you're flying, there are a range of propellers in terms of diameter and pitch you could experiment with. But what's important is that with the advances in propeller technology these days, there are some pretty exotic shapes to these propellers. It is entirely possible to put the propeller on backwards. I've seen this a lot at the field because it's not necessarily completely obvious what is the front of the propeller. The easiest way to determine the front of the propeller is there is some writing near the hub of the propeller that gives the size of the prop and other information. I'll show a picture up here of a detail of what this looks like on here. And the key is this writing should always face forward on the aircraft. If this prop is installed backwards, this etching on the prop will be towards the rear of the aircraft. You don't want that. Also, you notice an example I showed, it was a 10x7E. The E stands for an electric prop. The electric props are a little bit less strong than the ones for gas-powered engines, but that's okay for the electric-powered flight. The other thing is, occasionally I've seen props mounted that are a P. The P stands for a pusher prop. There's a lot of pusher props out there with flying wings. If you have a pusher prop mounted regularly on a normal airplane, it won't work well. And if you have a prop on backwards, the reason it can be a little bit tricky, you'll still get thrust from that prop. It'll be about 1/3 the thrust of a prop mounted correctly, and there'll be a loud buzzing sound. So if you have a engine, battery, and it just seems like it's a weak setting, check to make sure the prop is on correctly. Color schemes are important for your model as well. We like to have distinctive color schemes for our models. On my F-22, even though this is not a real F-22 color scheme, it's from the F-15 Aggressor Squadrons out at Nellis Air Force Base. I think it was an attractive scheme for this airplane. The problem is, with this airplane, the color scheme can blend into a blue sky. You might not see it as correctly, vividly. So what I did in this case was I kept the bottom white, and I added some tape just to add some contrast to the model for orientation purposes. Where this approach can be useful, there are models out there, especially flying wings. It's very hard to tell the orientation, especially with not a lot of vertical tail surfaces on there. So do keep an eye on your color scheme. Make it as vivid as possible, contrasting as necessary, so you can keep orientation of your model. Another common mistake is not having fully charged batteries. So we all have our collection of lipo batteries, and what I do for my technique is any battery that I take to the field is fully charged before I leave the house. I've seen many others that charge their batteries at the field. They might not be able to do it the day prior. I've seen some devices with this little slider on the side between a red and a green for charged or not charged. The reason it's just important to have those batteries charged, you might have a battery where you flew a couple of minutes, it's partially charged, you forget if it's charged or not, you plug it in, the plane will work, everything flies. I build in a timer onto the transmitter, but the timer assumes the battery is fully charged. If you take off, plan to fly a full flight, the battery is only half charged. It could lose its full charge halfway through your flight. Depending on how it's set up, it's just a bad thing when an electric-powered model loses its batteries for controls and getting back to the field. So always make sure your batteries are charged. I charge them before I go to the field. Remember, we have two sets of batteries. We have the batteries for the transmitter as well as the in-flight. And so in this case, I have a Spectrum DX6. There are AA batteries that are in this transmitter. There's a very easy read right here, 5.2 volts. And what I do from the manual, I just have a little reminder down here, 4.3 is the absolute minimum voltage for this transmitter at the field. I have a spare set of batteries, so I have to swap that out. And I try to discipline myself every time to take a look at that voltage to make sure that it is above 4.3 volts. Another key thing to do is a control surface check. Every time before you take off, you should do a control check. Elevators, ailerons, rudders, to make sure that they are free and unobstructed, they move in the proper direction, and you're good for flight. There have been any number of airplanes after a maintenance, fiddling around to the radio, controls are reversed. And when you have, for example, reversed ailerons on a takeoff, it happens so quick, there's not anybody out there that can catch that in time. And keep in mind, maybe somebody fiddled around with the radio, there was some change. Even if you are flying the model consistently, maybe a set screw got loose that maintains the movement of the elevator or rudder. Just make sure those controls are free and they move in the proper direction before any takeoff. The next important or mistake you want to avoid with RC model flights is make sure you do a range check on your radios. Now, with the modern radios these days, especially the Spectrum DX6, this is the antenna. In the old days, we had these long extended antennas. They could have broken wires and so forth. And to do a range check, you literally had to turn on the radios, have somebody pace for a distance to make sure that the controls worked at some distance. The newer radios have solved this with a range check. So let me show you how on this DX6 we can quite easily do a range check using one of the built-in range check function. We simply turn it on. This is the F-22. I click on the side to the function list, and I just scroll down until I get to range test. I click that, and what happens, this is range test full power, and the test distance is 30 meters, or about 30 paces. But on the top, we have the bind switch. When I push the bind switch, it goes from full power to reduced power for the range check. By holding it at reduced power, and the model is just 30 meters away, which is not very far at all, when you move the control sticks and everything works okay, that is a demonstration that the range is proper for flying the model when you're at full power without the range test. It's absolutely vital that your wing is free of warps as well as your tail surfaces, but the wing is the main thing. Very often when we have balsa covered wings, over time the covering can tighten in one area or another, or it can just be a change in the shape of the wing. Just look at it to make sure that it's flat. With the iron-on covering, it's very easy to twist it one way with a heat gun, shrink on the covering to take out the warp. Any warp in a wing will hurt the performance of the aircraft. Very often with our almost ready to fly models with their foam wings, this is something you don't have to worry about much at all. You'll understand how strong your wing is when you fly it, but you just have to make sure there's no warps in either your wings or your control surfaces. The next item is airspeed. The most important thing when you're flying an airplane safely in the landing pattern is control of your airspeed. And this is an important thing to emphasize with models because the airplane senses airspeed when it flies. However, we're on the ground watching that airplane and we tend to relate it to ground speed. So for an example, just imagine you had an airplane that flies at 20 miles an hour. That plane is flying 20 miles an hour. The wind is going 20 miles an hour. The plane will hover. It will have zero ground speed because it's going 20 miles an hour this way, airspeed, the wind 20 miles an hour. You can literally fly it directly over the ground. At the end of this little segment, I'll show you my Blackburn monoplane, one of my designs. The design to fly very slow. You'll see it basically hovering to land because it's flying into a light breeze, but it can fly very slowly. So keep in mind, it's zero ground speed in this situation, even though the airplane is perfectly happy, safe, and flying at 20 miles an hour. If we circle around and go downwind, now the plane is going this way at 20 miles an hour with the wind behind it at 20 miles an hour. So the ground speed in this case is 40 miles an hour. So the plane appears to be going fast at 40 miles an hour ground speed, but if you were in the cockpit of the model, the airspeed would be 20 miles an hour. So it could be a little bit confusing where it would go very fast on downwind, 40 miles an hour ground speed, but as you turn into the wind in this example, it goes to zero ground speed, even though everything's okay. You just have to discipline yourself to understand that airspeed is important. It will appear to be going faster on the ground when you're going downwind, when you're going into the wind a little bit less. And if in doubt, just add a little bit of power with the models. That will usually give it a little boost with the airspeed. This is my Blackburn Type D 1912 monoplane. Plans and construction video on the site. Nose are taking off into the wind. Here we are landing. The airspeed is fine. There's a little bit of a headwind. The plane is fully under control because it's flying airspeed, not ground speed. You can see it almost hovers down to a touchdown on the runway. Again, a slow flying model, but the point remains the same on ground speed versus airspeed. Well, previously we gave 10 common errors in radar control flight. I'm going to give you a bonus. It's not really an error, but just something to keep in mind. That is the use of checklists. This is a field box checklist that I use on my own. I'll give an example up here of what I use. It's just a simple checklist when I go to the field to make sure I bring everything from the field box to the transmitters to the batteries to the chargers. It's always interesting when you show up in the field. You forget your sunglasses, a hat, a bug spray, wings for the aircraft if they're rubber banded on. I just like to run this right before I launch out to the field to make sure that I have everything that I need. So thank you for joining me in this video. These are some of the 10 common errors for radar control flight. If you can keep track of these things, learn from them and not do them, you could avoid a crash, save yourself some money, and just have more fun at the RC flying field. Thank you for joining me, and we'll look forward to seeing you in the next video.